Next we move on to linear regression model and their properties. So these are the assumptions that come under the classical linear regression model. So we'll discuss one by one. So linear in their parameters. So a classic regression model is equal to yi is equal to beta 1 plus beta 2 xi plus ui. So xi is the independent variable, yi is the dependent variable, beta 1 and beta 2 are the parameters, and ui is the error term. So this is an example of a classic linear regression model. So this particular regression model, the first assumption is it is linear in its parameters. So this model, as you see here, is linear in its parameters. So that is the first property. Secondly, the x values are fixed. So when you take, it's given xi, so it will be x1, x2, x3, etc. So when you take repeated sampling, this particular x values would be fixed. So that is the second assumption. So it is basically conditional. So expectation of yi will be conditional, y will be conditional on the values of x. So y will change depending on the values of x. So x values will be fixed. The third property is zero mean value of the disturbance ui. So this particular term is either called the error term or the stochastic term or the disturbance term. So these are basically the values that depict the disturbance term. So zero mean value of disturbance ui means that expectation of ui given xi is equal to 0. So mean value of disturbance ui is 0 is symbolically represented as expectation of ui or the average value of ui given the value of xi is equal to 0. So that is the third assumption. Fourth assumption is homoscedasticity. Homo means equal and scedasticity means spread. So this particular regression model has an equal spread or otherwise called a uniform variance. So it is symbolically given as expectation of ui square is equal to sigma square. Sigma is nothing but the variance. So homoscedasticity indicate a uniform variance in a classical linear regression model. And the fifth point is there is no autocorrelation. So what is autocorrelation? Autocorrelation is basically a covariance existing between the error terms. So covariance is basically the variance between two terms and these are the error terms. So if there exists a covariance between the error terms, then it is supposed to be an autocorrelation, but in a classical linear regression model there is no autocorrelation. So covariance of ui uj is equal to 0. So these are the first 5 assumptions of classical linear regression model. It is linear in its parameters. The x values will be fixed in conditional or repeated sampling. 0 mean value of disturbance ui, that is expectation of ui given xi is equal to 0. It is homoscedastic, that is there is only uniform variance. So expectation of ui square will be equal to sigma square, and there is no autocorrelation, that is covariance of ui uj is equal to 0. Further, when we discuss the remaining 5 points, there will be one point called multicollinearity, and these autocorrelation, multicollinearity, etc. tend to show a bias when you take realistic samples. So all those exceptions to the classical linear regression model we will discuss in the coming videos, but as of now these are the assumptions related to classical linear regression model. We move on to the sixth assumption. There is zero covariance between ui and xi. So basically there is zero covariance between the error term and the explanatory variable. So that is the sixth assumption. And the seventh assumption is the number of observations n must be greater than the number of parameters to be estimated. So this in other words can be explained as the number of observations n basically must be greater than the number of explanatory variables in the model. So the number of observations n must be greater than the number of parameters, which in other words is nothing but the explanatory variables in the model. And variability in x values. So earlier we discussed that in a repeated sampling the variability or the x values should not remain the same, but within a particular sample there must be variables, there must be variability in x values, otherwise the model will not hold good. So within a particular sample there must be variability in x values, and in repeated sampling the x values need not be the same. And the regression model is correctly specified, which means that there shouldn't be any specification error with respect to a classical linear regression model. And the last assumption is there is no perfect multicollinearity. So what does multicollinearity mean? Multicollinearity is nothing but there will be relationship or correlation between the explanatory variables within a model. So y is equal to beta 1 plus beta 2 x2 plus beta 3 x3 plus ui. So in this particular 3 variable regression model, x2 and x3 are the explanatory variables. So ideally these x2 and x3 must not be correlated or related to each other. So these variables must be independent of its nature. So in case if there is a relation between x2 and x3 or the independent variables or the explanatory variables, it is said to be multicollinear. So that kind of multicollinearity shouldn't be there in a classical linear regression model for the model to hold good. So that is the assumption. So but these 3 assumptions of heteroscedasticity, autocorrelation and multicollinearity tend to change when it comes to real life examples. So those changes and what happens when these assumptions does not hold good, we will discuss in the coming videos. So we have seen the assumptions related to the classical linear regression model. Now we move on to the Gauss-Markov theorem, otherwise called BLUE. So BLUE is basically best linear unbiased property of estimator. So say in a classical linear regression model, beta 2 cap, the OLS estimator beta 2 cap is said to be blue. When is it said to be blue? So when it is linear, unbiased and it has the minimum variance. So it is said to be linear if yi is equal to beta 1 cap plus beta 2 cap xi plus ui. So in this particular classical linear regression model, beta 2 cap is linear. It is said to be unbiased if expectation of beta 2 cap is equal to beta 2. That is, the expected or the average value of the estimator beta 2 cap is equal to the true value of beta 2. In that case, the estimator beta 2 cap is said to be unbiased. So it's linear, it's unbiased. And third property is minimum variance. So the variance of beta 2 cap in this particular model should be minimum. So in this minimum variance property is otherwise called efficient. So it's either minimum variance or the variable or the parameter beta 2 cap is said to be efficient. So the Gauss-Markov theorem or BLUE basically states that given the assumptions of CLRM is nothing but classical linear regression model, the least square estimators in the class of unbiased linear estimators have minimum variance. That is, they are blue. So basically, given the assumptions of classical linear regression model, those are the assumptions that we discussed earlier, the 10 assumptions related to classical linear regression model. So given those assumptions, the least square estimators in the class of unbiased linear estimators have minimum variance. That is, they are blue. So that is, there will be best linear unbiased estimators. So we have already discussed the assumptions regarding the classical linear regression model. So these are the exceptions to 3 of those assumptions. So one is homoscedasticity, one is autocorrelation and one is multicollinearity. So what happens when these assumptions does not hold? So first one is an exception to homoscedasticity. So homoscedasticity, as we earlier discussed, it is uniform variance. So what happens? So we said that expectation of ui square will be equal to sigma square. There will be a uniform spread or uniform variance. So what happens if it does not hold true? What happens if the variance is not uniform? The expectation of ui square will not be sigma square, but instead it will be sigma I square. So expectation of ui square will be sigma I square, would be the symbolic representation of the condition of heteroscedasticity, where hetero means different and scedasticity is the spread. So unlike homoscedasticity, which is uniform or equal spread, heteroscedasticity is different or unequal spread. So there are few tests to detect heteroscedasticity, which is Spearman rank correlation, Goldfed and Quant, Gleiser test and Park test. So these tests and the consequences of the OLS estimators, if we continue the estimation irrespective of the existence of heteroscedasticity, are very important in terms of the examination point of view. These are often asked, the test related to heteroscedasticity and the consequences of the OLS estimators if we continue the estimation without correction of heteroscedasticity. So what are the tests? Spearman rank correlation, Goldfed and Quant, Gleiser test and Park test. So these are the tests used for heteroscedasticity. And the consequence of the estimators are, it will continue to be consistent. If we continue the estimation without correcting for heteroscedasticity, the estimators will be consistent, unbiased and inefficient. So we know that it will be unbiased and consistent, but inefficiency, why? Because efficiency is when the estimators have minimum variance. Here the variance will not be uniform, so variance will increase. So the estimators will be inefficient. So consequences are consistent, unbiased and inefficient. So these are the properties with respect to heteroscedasticity if the assumption of homoscedasticity does not hold good. So moving on to the next exception under the classical linear regression model, here it's autocorrelation. So earlier we assumed that there is no autocorrelation between the variables in a classical linear regression model. So autocorrelation is when you assume that there is no autocorrelation, it is said to be that there is no covariance between the error terms. So covariance of ui uj will be equal to 0 if there is no autocorrelation in the model, but here we have autocorrelation. This is an exception to the assumption that there is no autocorrelation. So here there is autocorrelation, so the covariance between ui uj will not be is equal to 0. So the test used to detect autocorrelation is Run's test, Durbin-Watson and Brouwer-Godfrey. Of these, Durbin-Watson is the most commonly used test, and questions are also most commonly asked based on Durbin-Watson test. So the formula for Durbin-Watson is D is equal to 2 into 1 minus rho, where rho lies between minus 1 and plus 1. So rho is nothing but the correlation coefficient. So what will be the value of D? Rho is equal to minus 1, rho is equal to 0, rho is equal to plus 1. So when rho is equal to minus 1, D is equal to 2 into 1 minus minus 1 is equal to 4. When rho is equal to 0, D is equal to 2 into 1 minus 0 is equal to 2. And when rho equal to plus 1, 2 into 1 minus 1 is equal to 0. So when rho's value lies between minus 1 and plus 1, putting those values in this equation, we get D's value to lie between 0 and 4. D lies between the Durbin-Watson statistic. The Durbin-Watson statistic D lies between 0 and 4 when the correlation coefficient rho's value lie between minus 1 and plus 1. So that is the test, most commonly used test to detect autocorrelation. And the consequences. So these are the consequences of the estimators if you continue the estimation disregarding autocorrelation in the model. So the hypothesis test could lead to wrong conclusions. Without correcting for autocorrelation, if you continue the estimation, the test could lead to wrong conclusions and the standard errors would be inappropriate. So these are the two consequences if you disregard autocorrelation. So the assumptions of CLRM model, the classical linear regression model, assumes that there is no multicollinearity between the variables. So what do you mean by multicollinearity? Multicollinearity is when there is interrelationship or when there is correlation between the explanatory variables. x1, x2, x3 are the explanatory variables in this particular multivariable regression model. So when there exists correlation or relationship between the independent variables in this model, it is said to be multicollinear. So usually we assume that there is no multicollinearity between the variables, but the exception to that is there exists multicollinearity between the variables in the classical linear regression model. So what are the tests that we employ to identify or detect multicollinearity? Frisch confluence and Farrar-Glauber are the tests used to test multicollinearity. And what happens if you continue the estimation disregarding multicollinearity in a model is the estimators will continue to be consistent, it will be unbiased and it will be efficient. So the consequences of disregarding multicollinearity is basically very less because the estimators will continue to be consistent, unbiased and efficient irrespective of the problem of disregarding multicollinearity. Now moving on to the previous year questions under this section. To December 2018 paper 2 98th question, it is a match the following question. So we have these items in list 1 and these following items in list 2. So Delphi method, Dickey-Fuller test, Durbin-Watson, student t-test, stationarity, autocorrelation, testing significance of a regression coefficient and forecasting. So how do we match this? First one is Delphi method. Delphi method is used for forecasting. So A would be 4. So A would be 4. Delphi method is used for forecasting. Dickey-Fuller test we already discussed in time series that it is used for stationarity. Dickey-Fuller test and unit root test are both the test used to detect or understand stationarity. So this is stationarity. B is 1. Durbin-Watson is the test used for autocorrelation. So C would be 2. and student's t-test is for testing the significance of a regression coefficient. So D will be 3. So Delphi method is used for forecasting, Dickey-Fuller test is used to detect stationarity, Durbin-Watson is used for autocorrelation or otherwise called serial correlation, and student's t-test is used for testing the significance of a regression coefficient. So the next question is 2018 July paper 2 95th question. Match the following. So we have these items: contingency table, unit root test, Fisher's F-test and Granger test in list 1, stationarity, causality, chi-square test and test of significance of overall regression in list 2. So matching these, contingency table is associated with chi-square. So A is 3. In fact, the contingency table of chi-square is calculated as CT is equal to R minus 1 into C minus 1. So R is the number of rows and C is the number of columns. So that is contingency table. Unit root test is related to stationarity. So B is 1. Unit root test is used for stationarity. And Fisher's F-test, it's a sampling distribution test and it is used to test the significance of overall regression. So C will be 4. So F-test is used to test the significance of overall regression. And Granger test is used for causality. So D is 2. Granger test is used to study the causality between the variables. So moving on to the next question, July 2018 paper 2 96th question. Generalized least squares or GLS method of estimation will not be suitable for dealing with which of the following problems: autocorrelated disturbances, heteroscedastic disturbances, multicollinearity and errors in variables. So usually in classical linear regression model we use OLS method, ordinary least squares. It's the principle goes that the least squares should be minimum. That is the ordinary least squares principle, and that is what is commonly used in a classical linear regression model. So the question here is, in which of the following is GLS not used? So for that we need to know that in which of the cases GLS is used. So instead of OLS, in some cases we use generalized least squares when there is heteroscedasticity and when there is autocorrelation. So for autocorrelated disturbances and heteroscedastic disturbances we use GLS method, and for multicollinearity and errors in variables we use OLS method or ordinary least squares. So here they have asked that in which of the cases is GLS not used. So it's multicollinearity and errors in variables. So for looking for those options we have C and D. So option C would be the answer. Multicollinearity and errors in variables are the two cases where generalized least squares is not used. So option C would be the answer. So next question, November 2017, paper 3, 73rd question. If a Durbin-Watson statistic takes value close to 0, what will be the value of first order regression coefficient? So it's given in the question that Durbin-Watson statistic is close to 0. What will be the value of first order regression coefficient or rho? Close to 0, close to 1, close to -1, close to either -1 or +1. So we have the Durbin-Watson equation as D is equal to 2 into 1 minus rho. So we know the value of D. D takes value close to 0. So say D is equal to 0. 0 is equal to 2 into 1 minus rho. So we have 0 is equal to 2 minus 2 rho. Taking 2 rho to the side, 2 rho is equal to 2. So rho is equal to 2 by 2 is equal to 1. So rho takes the value close to 1 when Durbin-Watson statistic takes the value close to 0. So close to plus 1. Option B would be the answer. So the next question, 2017 November, paper 3, 74th question. What would be the consequences for the OLS estimator if heteroscedasticity is present in a regression model but ignored? So these are the conditions that we discussed under heteroscedasticity. What will happen to the OLS estimators if we continue the estimation disregarding heteroscedasticity? So we learned that these properties would be, if we disregard heteroscedasticity, the estimators will be unbiased, it would be consistent, and it will be inefficient. So in short, if we continue the estimation disregarding heteroscedasticity, the estimators would be unbiased, consistent, and inefficient. So in these options, only option that matches with these conditions is option C, the inefficiency. The first option says that it will be biased, but we know that it will be unbiased. Second option states that it will be inconsistent, but we know for a fact that it will be consistent. And last one states that it's all the above. So it's these two options does not hold good. So it will be inefficient. That is the only criteria that satisfies the condition that if we disregard heteroscedasticity, these properties will follow. So option C would be the answer. Next question, 2016 July, paper 3, 74th question. It is a match the following question. So we have these items: goal-fed quant, Durbin-Watson, Farrar-Glober, and Wald-Bartlett test on list 1, and the conditions on list 2. So what are these conditions this particular test are used for? So goal-fed quant test is used to detect heteroscedasticity. So option A would be 2. Goal-fed quant test is used to test heteroscedasticity. Durbin-Watson test is used to test autocorrelation. We have discussed that earlier. Durbin-Watson is used for autocorrelation, or otherwise called serial correlation. Farrar-Glober test is the test used to detect multicollinearity. So C is 4. Farrar-Glober test is the test used to detect multicollinearity, and Wald-Bartlett test is the test we haven't discussed so far, but it is the test used to detect the errors in variables. So Wald-Bartlett test would be 1. So goal-fed quant test is for heteroscedasticity, Durbin-Watson test is for autocorrelation, Farrar-Glober test is for multicollinearity, and Wald-Bartlett test is for errors in variables. So the next question, June 2015, paper 3, 70th question. The term best in the best linear unbiased estimators blue implies. So this here they are talking about the Gauss-Markov theorem we have already discussed. It's nothing but the blue theorem which explains the best linear unbiased nature of an estimator. So what does this best linear unbiased estimator indicate? Maximum variance, minimum variance, average variance, or unbiased variance? So earlier we discussed that best linear unbiased means the estimators would be linear and estimators would be unbiased, meaning the expected value, say beta 2 cap is the estimator that we are talking about. Beta 2 cap will be linear, and it is unbiased means that expectation of beta 2 cap is equal to beta 2. So it is unbiased indicates that the average value of beta 2 cap will be equal to the true value of beta 2. That is the meaning of unbiasedness. Now what is best? Best means that the estimator will be efficient. Otherwise it is described as the estimator will have minimum variance. So what that goes with these options is not maximum variance, not average variance, not unbiased variance, but minimum variance. So best linear unbiased estimator indicate that best word is for minimum variance or the efficiency of the estimator. So the option 2 would be the right answer for this question. So the next question is June 2014, paper 3, 70th question. The sources of autocorrelation among the following are. So what are the sources of autocorrelation? Which of these following could lead to autocorrelation? The first one is omitted explanatory variables. Second one is interpolation in the statistical observation. Third one is misspecification of the true random term V. And the last one is economic variables to move together over time. So autocorrelation is basically the covariance between the error terms. So the economic variables moving together over time has no relation between the happening of autocorrelation or not. So the other three variables, omitted explanatory variables, interpolation in the statistical observation, and misspecification of the true random term, these three could lead to autocorrelation. These three, 1, 2 and 3. So option B would be the answer. So the sources of autocorrelation would be omitted explanatory variables, interpolation in the statistical observation, and misspecification of the true random term V. – 2013 June paper 268 question. In the presence of heteroscedasticity, the best linear unbiased estimators, or the blue, are provided by the method of ordinary least squares, indirect least squares, weighted least squares, and instrumental variables. So when there is usually in classical linear regression model we use the ordinary least squares, which is OLS. So when there is heteroscedasticity, to make it still a best linear unbiased estimator, which is the measure that you use? So it's nothing but WLS. Weighted least squares is used when there is heteroscedasticity in the model. So option C would be the answer. So moving on to the last question of this section, 2012 June paper 3, 54th question. In the presence of heteroscedasticity, which of the following is not a correct statement? So if the model has heteroscedasticity, which of the following is not true? Heteroscedasticity does not alter the unbiasedness and consistency properties of OLS estimators. So we have discussed earlier that if there is heteroscedasticity and we disregard heteroscedasticity and continue with the estimation, the model would be consistent, unbiased, and inefficient. So what they have told here is true. The model will be unbiased and consistent. So this particular statement is true. OLS estimators are of minimum variance or efficient. We'll come back to option 2. Moving on to option 3, blue estimators are provided by the method of weighted least squares. So blue estimators, if there is heteroscedasticity, is found by not OLS, ordinary least squares, but instead by weighted least squares. So this is also true. And T and F test based on standard assumptions of classical linear regression model may not be reliable. So if there is heteroscedasticity, using T test or F test may lead to wrong results. So that is what is meant by this statement. So this is also true with respect to heteroscedasticity. The only wrong statement here is the OLS estimators are of minimum variance, because this is the normal blue condition if there is homoscedasticity. If there is heteroscedasticity, the variance will not be minimum, it will be inefficient. So this particular statement is false. So option B would be the right answer. So with this we have come to an end of the section, linear regression model and their properties. So we have discussed the previous year questions and the concepts under this section. So please like our YouTube channel and subscribe for more videos, because more videos are yet to come. Thank you.